Today we are going to show you a presentation on seismic data modeling, which is quite a new breakthrough technology in near-surface seismic. Previously, this technology was only available for oil and gas market, but now construction, mining, ecology, safety, and other areas of seismic studies are coming to the fore. So we, together with the leader of seismic data modeling software, Tesseral Technologies Inc., have created and adapted project specifically for shallow exploration. Please meet Tesseral Engineering software. Several slides about our companies. We are international multi-method geophysical equipment manufacturing company with 3 offices in different parts of the world. We are producing land and the marine magnetometers, susceptibility meters, electrical resistivity or electromagnetic systems, and seismic systems as well. We have representatives in different parts of the world. You can find all contacts on our website. And I want to show you just a few slides of the equipment to make it clear why we ourselves need a seismic data modeling project. This slide shows the equipment for ultra-high resolution marine seismic. This is energy source, different types of towed sources, and towed streamer and bottom streamer. And with this equipment, we can obtain seismic sections with a unique resolution in the water area. You can see very broadband spectrum and scale in meters. So the spectrum is more than up to, let's say, 7 kilohertz. It's a unique broadband spectrum for ultra-high resolution marine seismic. And most importantly, very clear boundaries. Without a deep understanding of the processes with modeling and a large number of tests, we wouldn't have been able to achieve such a result. This is another beautiful example with Sparker. Previous one was have been done with Bloomer. So it's also very broad. It also has very broadband spectrum. Up to 9 kilohertz here, and very clear boundaries and scales in meters. Here, and between marks, it's only 5 meters. So they have really unique resolution. And next slide about our next seismic project, hardware project, is about equipment for high resolution borehole seismic techniques for near surface application, mostly. Let's say for maximum 1 kilometer depth. Usually it's much less, up to a couple hundred meters, but we can do a bit deeper. Here you also see energy source, different types of borehole sources and borehole receivers with geophones, free component, and hydrophone streamer. And again, excellent sections obtained by the method of cross-hole seismic tomography here. Obviously, obtaining such data requires not only good equipment, but also an understanding of optimal system of observation, as well as very careful processing. Tesseral Technologies was founded in Canada, Calgary, in 1997, so 25 years ago. Now Tesseral is a global leader in full wave modeling. For 25 years, hundreds of geophysicists in more than 30 countries of the world have been using Tesseral software products. Until recently, the main focus of the company was the oil and gas market with advanced Tesseral Pro software. But with the advent of Tesseral Engineering, everything is changing. Tesseral Engineering is customized for near-surface surveys It is much more affordable version of the world's most popular oil and gas full wave modeling software package, Tesseral Pro. The program allows to simulate the field seismic data for media of any complexity in order to test the capabilities of the selected acquisition system for geological problem solution. Modeling at the work planning step enables to determine the optimal acquisition system, and at the interpretation stage to make sure that it is adequate and reliable for particular problem solution. Tesseral Engineering works only with 2D models of any length, depth up to 300 meters, and maximum number of channels in the active spread equal to 101, which is more than enough and covers almost the entire range of shallow seismic tasks. So, short comment about what does mean maximum number of channels in the active spread equal 101. Well, for every source, we have some limitation, and Tesseral Engineering is only 101 channel for each shot point, but we don't have any limits for numbers of number of shot points. So the entire channels in your seismic data modeling are not limited. And here the main limitation is only 2D. Mostly, I would say that it's the main limitation in of Tesseral Engineering. In Tesseral Pro, we don't have such a limitation. It's 3D, no limitation in depth of the model and quantity of channels. So it's, but for near surface tasks, Tesseral Engineering is good enough, and it's much more affordable than Tesseral. Let's understand together what types of modeling are available and what seismic data modeling is. Modeling is a solving of forward seismic problem. This means that we create a model of the geotechnical environment, impose a system of observation, determine the source signature, the type of the sources, and their parameters to reconstruct the wave field attributes. It means that we calculate seismic gathers as if we get them in the field on the same model. There are kinematic, ray tracing, and full wave modeling. Kinematic modeling is marked with an asterisk because this type of modeling doesn't give us a seismic gathers, but it's simple and often used in data analysis and data processing. I mean here mostly, of course, refraction seismic, tomography, let's say, where we need to mostly just first breaks, cartographs, that's it. It is clear that there is 1D, 2D, or 3D modeling. It is also important to understand that the solution to a modeling problem can be exact or approximate. The most important part is understanding why we need modeling and how we can use it. The three most important areas are listed here. Also, there are actually more. So these are the first one is studying the connection between the structure of the medium and the structure of the wave field. Second is calculation of wanted wave and noise wave field to select and justify the survey methodology under specific conditions. And finally, is a comparison of the calculated wave field with the observed wave field during processing and interpretation stage to optimize the processing graph and increase the reliability of interpretation. Let's see how modeling can be applied. The photo shows a typical seismic data acquisition process in shallow seismic. This is a photo from the internet, and I really don't know what method they do with and what problem they solve. Let's imagine that the guys are doing MASW survey. The focus of such work is to obtain surface wave data for further processing and interpretation. The screen shows a typical seismic gather and a dispersion curve for surface wave. The processing of such data makes it possible to obtain a velocity section of shear waves. MASW is a very popular and common method in near-surface seismic surveys. I'm sure that you understand what I'm showing here. The only nuance, perhaps not very obvious, is the field data was simulated, and the model is shown here on the screen. We created this model and calculated seismic gathers in Tesseral Engineering. Then we processed them in ZoneTest-2D software. Now we can compare the results and understand how good our processing is and how the given model and the reconstructed section correlate. We see that the ledge didn't recover very well. So this ledge. This is a bad feature of MASW, which smooths section in horizontal dimension. Probably here we can conclude that MASW is poorly suited for that model, and it is better to choose another method, maybe a cross-hole seismic tomography, maybe just regular seismic tomography, or reflection seismic. And the same result we obviously will get if you'll have any, let's say, sinkhole karst, small local object somewhere here. And so I'm sure that we will not get it in the same section as well, because it would be smoothed. And we also used this data for processing by the CMP cross-correlation method, CMP cross-correlation of surface waves. Here the resulting model is placed on the top. It is clearly seen that it matches the given model better, but still we have not a very good result in determining the position of the ledge. So if our target would be the ledge, in that case, MASW is not the best choice, right? And we can clearly see it through modeling. Another example of seismic data modeling. Here we tested the possibility of reconstructing different sizes of cavities with different fields in fractured limestone layer. This is cross-hole seismic tomography with 30 meters distance between boreholes. So on every model, we have 2 boreholes, sources and receivers, and let's say sources and receivers on the top. And between boreholes, we have only 30 meters. And borehole depth is 55. In cross-hole seismic tomography, we use sources in one well and receivers in another. This allows to get a lot of seismic rays for the reconstruction, of course, of high resolution cross sections. In such works, in near surface projects, sources and the receivers in the borehole are usually located with a spacing of 1 meter only. Left picture shows the synthetic model. This is a synthetic model without cavity. And this is result of its reconstruction. We don't have any cavity. The cavities here, they have only a bit smooth boundaries, which is kind of normal for seismic tomography. And here we placed in the model, in a synthetic model, some cavity. And this is a result of its reconstruction. So we see boundaries and good velocity model and cavity as well. And the right picture shows a different section for reconstructed models. We see just evolution of the model. Here we wanted to show that in the case of karst fusion processes, periodic observations in the same boreholes with subsequent calculation of the different sections will obviously help to track the evolution of the medium in detail. This is a kinematic modeling in zone T2D. We calculated the hadographs and made first breaks tomography to reconstruct the models. It is clearly seen that the models are quite good. But in this work, we do not know anything about the frequency of the signal. It is well known that the resolution of in seismic exploration directly depends on the frequency of the recorded signal. How we can understand whether we would get this nice result in practice or not. Let's see another example. The modeling that I showed you on the last slide, it was preparatory work for a large project to detect small-sized cavities. So they have small-sized cavities here. So, and a rather complex section. Shown here is a more complex model and the result of its reconstruction, as well as the calculated velocity gradient here. The distance between boreholes for this result of seismic tomography inversion, the distance between boreholes here was only 20 meters. And we have nice cross-hole section with cavities, with good, very nice velocity model. And here we tested increased distance between boreholes, 100 meters between them. And we don't see any cavities here. We still see quite a good velocity model, but not cavities, no cavities at all. And the result is noticeably worse here. So it's a conclusion. But again, we don't know anything about frequencies. And what can we do about it? Is it possible to get such result on real project or not? To reconstruct all these small and local objects or not? Let's imagine that we have two boreholes, source and receivers in them. Schematically shown here. So this is the source, and this is sources and receivers. And we consider array from the lower source to the upper receiver. Many of you have heard the term of the Fresnel zone. It describes the resolution in reflection seismic. In tomography, we use the first arrivals, and for such waves, there is the term of the Fresnel volume. This is the volume which seismic energy travels, which forms the first phase of our signal, first breaks as well. The formula for calculating is quite simple. This is the formula. And if we start to calculate the size of the volume, the diameter of the volume, it becomes a little scary, and it is not clear how in cross-hole seismic tomography we can even get a high resolution. So if diameter of Fresnel zone is several meters or more than 10 meters, 20 meters, so it's quite big, right? And for 20 meters only between boreholes, and this configuration of source and receiver, the diameter of the Fresnel volume would be 7.5 meters. And yeah, because in formula we have distance between the length of the ray and wavelength as well. It's important to notice that velocity in the model is 2,000 meters per second, and signal frequency is central signal frequency was set as 1 kilohertz, and 7.5 meters is quite a lot if we consider that this is a kind of limit of our resolution. Let's figure it out. In seismic tomography, there is no information about signal frequency. We decided to apply the full wave modeling in order to test the dependence of tomography resolution and the recorded signal frequency. To achieve this goal, we created a set of simple 2D synthetic models with a homogeneous half space and small cavity, 3 to 3 meters, which was placed approximately midway between boreholes. We performed simulations for cross-hole seismic tomography and reverse VSP data for different source and frequencies. So the process of seismic signal propagation in the medium is shown on these pictures. For simplifying the analysis of these data, I would like to show you here cross-hole seismic testing sorted seismic gathers. It means that for every trace, seismic trace, we have a position of source here and receiver here, so on the same depth. And this kind of set of only horizontal rays. The source frequencies was 500 Hz, 1 kilohertz, and 2 kilohertz. We have modeled, of course, the full cross-hole seismic tomography and reverse VSP data, but it is impossible to show and compare them on the one slide. Here they show the synthetic model on the left and further the reconstruction results for the source at 500 Hz, 1 kilohertz, and 2 kilohertz, and tomography reconstruction according to kinematic modeling in Zone-2D software. So without any knowledge about frequencies, just kinematic modeling of photographs. It is well seen that the higher the frequency, right? The higher the frequency, the closer the reconstructed anomaly to the kinematic modeling result. So these sections are quite similar. We also calculated the velocity gradient. The slide shows the gradient sections in the same order. as in the previous slide. From left to right, there are the gradient for the synthetic model, gradient for source frequencies, 0.5 kilohertz, 1 kilohertz, 2 kilohertz, and for kinematic modeling. The conclusion that the higher the frequency, the closer the reconstructed anomaly to the kinematic modeling result is well supported. So these velocity gradients are quite similar. With this in mind, we are making our borehole sources as high frequency as possible to achieve really high resolution. This allows to our customers and clients to get really very high resolution sections on real projects. These cross-hole seismic tomography compressional velocity sections are obtained at the site of the nuclear power plant proposed location. It was a detailed study of the tectonic structure and the identification of possible tectonic dislocations. The distance between borehole was from 15 up to 30, maybe a bit more, let's say up to 35 meters, and depth of almost all boreholes was about 150 meters. For some of them, it was a bit less. But yeah, anyway, we have really nice resolution here. Let's understand what full wave modeling is. As part of solving this problem, we solve the wave equation to calculate the full wave field. As a result, we get a snapshot of wave field and seismic gathers. In Tesseral Engineering, we can see the created model, wave fields, and seismic gathers at the same time. We will see it when Roman will demonstrate to us seismic. Tesseral Engineering software, and let's take a look at how we can set up a full wave modeling and what are the main parameters. The first is the type of wave equation. Here, depending on the type, we must set more or less parameters for the model. The most advanced is elastic modeling. There are where we have to set the velocities of the compressional and shear waves, as well as the density of the rocks. And next, you must create a model. In other words, determine the position of the boundaries and set parameters for them. In fact, we can also specify porosity, fracture, fluid type, and anisotropy. Then we must define source type and set its parameters, and then create a system of observation. In addition, we must specify the discretization of the model. It may sound complicated, but it's not so difficult. Let's see how this is done in Tesseral Engineering using the simplest model as an example. So I think that it's a good point to show Tesseral Engineering. Roman, would you please share your screen?
Okay, hello, everybody. And in my part, I want to demonstrate how to obtain data in the program Tesseral Engineering. The program welcomes us with a window in which it is offered to set the size of our future model. Two values are used to set the size of each of the model along each axis, and the program has reasonable limitations on the size of the model, since this is, after all, a version for engineering research. For the first model I want to show you today, let's leave the default values. So 1,000 meters your x-axis and 300 meters their z-axis. Okay, after that, the program creates the first polygon over the entire model area and opens the model editing workspace. And the first polygon will also be our top layer in our model. Also, subsequent layers we will draw with polygons on the top on the first one. Okay, let's move on to the editing of the first polygon characteristics. Let's set up the properties. And here, I want to draw your attention that the programmer already has a list of the most common rocks with a set of typical characteristics, which is very convenient for work. And as a reference, here we can set up the velocities of compressional and shear waves, rock density, and some other characteristics. But for our purposes, let's choose between the standard ones. So let's start filling our model. The first layer, for example, will be a leverlight. And I can simply apply the typical characteristics for a leverlights from the list. And also I can apply the pattern for a leverlight. We can also set a different pattern for each rock to make our model look more geological. And of course, we can choose our own characteristic for rock, and we can load our own patterns. Now that the first layer is ready, let's move on drawing and fill in the remaining layers of the model. Let's draw the second layer. The first boundary at the depth of the 40 meters. And after I finish drawing polygon, the program opens the window for editing the polygon model, the polygon characteristic automatically. Second layer will be, for example, marl. Let's apply characteristics and pattern. And as you can see, each polygon will be colored corresponding to the color of the longitudinal wave velocity on the scale on the right side of the screen. Let's draw the next layer. The next layer will have a fold in it. Let's draw the fold like this. And it can be a sandstone, for example. And let's add 2 more layers where the fold will continue. Next layer can be, like, for example, light. And the last bottom layer, let's draw it first. This could be sandstone, but with a higher velocity parameters. Okay, as you can see, we need to edit last polygon, and we can easily do it with adding 1 more node and dragging it to the desired position. The fold zone itself characterized by reduced velocities. So let's draw a polygon which will reflect our fold zone. Let's define the compression wave velocity lower and corresponding to the layers around it. And our model is built, so we can proceed to the spacing parameters. Here is in the framework window, we can specify the location of sources and receivers and other settings. And for our purposes, let's calculate the model for a single source position to make it less time consuming in computations. As you can see, you can choose between different source types like omnidirectional source or monopole or dipoles, and define the array parameters. On the next step, let's set the position of receiver line. Let's set the receivers from 100 meters to 900 meters with a 10 meters interval. And in the right part of this window, we can also set the registration parameters. Let's limit our recording time to 0.3 seconds and choose the sample rates. So we will have around 1,000 samples per seismic trace. Here we can also specify snapshot parameters. So let's have snapshots from 0 second. With this step, so we will have 61 snapshots per each source position. In the signal tab, you can also set the parameters of the seismic signal, such as type of the signal. It has different built-in signal forms. And you can also choose user-defined signal to define your own form of the signal. Also, you can change the peak frequency, amplitude, and phase. And that's all. As a model and setup parameters are set now, and we can do the calculations. Here you can set the type of the environment, 1-dimensional, 2-dimensional, and so on. And you can add the density and velocity of shear waves to the calculation, set the anisotropy of the medium. And on the right side of the dialog box, you can select the output data type. Let's choose geophones, 2-component geophones. And here on the bottoms of this dialog box, you can also specify the velocity range and the size of the medium cell. But the program selects these values automatically, so we will leave it default because it selects based on your initial model. Okay, to start the calculation, we can simply press run, and at this step, the program will ask us to save our model. After that, the calculation will start. As you can see, the software does the calculation relatively fast, even on my average performance notebook. And the program uses distributed calculation on the graphic cards. And now the calculations are done, and we can look at the result. Now we have 2 more windows below the model window. And in the left window, we can see the calculation gazers. And in the right window, we can see our model with the overlaid wave pattern for each moment of time, according to our snapshot settings. Before we can analyze these two windows, we need to adjust visualization options. Let's add more gain to see our seismic gazers better. And now we can move between the snapshots with a slider on the top of the window. And as we move between the snapshots, the red line on the left part will show the exact moment of time, which will correspond to this snapshot. Moving between the images, snapshots, we can easily trace what the arrivals of each wave on the gazer corresponds to. For example, here is the first reflected wave comes in to our receivers, and the hyperbola for the reflected wave is shown on our seismic gazers, appears in our seismic gazers, and we can easily trace it on the snapshot window that it is a reflected wave from the first reflection boundary. Then we can see the waveform breaking up on the fault zone. And when it comes back to our receivers, it forms in two separate parts of hyperbola. Here and here. For the visualization options, I can draw your attention that here is a different advanced visualization options like gain or outer gain or some balancing and normalization. And also we can switch between gray visualization. We can turn on or off our traces, wiggle and wiggle. And also all the calculation data is saved to the folder with our project. So we can use this Segway data viewer to view and process in familiar programs. For example, we can take a look on our gazers that we have obtained now. And this is how the surface seismic data looks like in the presence of the large fault in the section, which looks pretty natural to me. And today I also want you to show another model I've built in advance. Let's see that it is a model for VSP method. And for VSP method, as you know, the receiving line is placed in the well, and the sources are at the surface. And here I placed the receiver line along the vertical line from 0 meters to 300 meters with an interval of 5 meters. And I wanted to show that you can place your setup array as you can imagine. So any setup is possible. And let's calculate this model. But here we will assume that we're working with hydrophones, for example. And let's calculate it. Okay, now we got our seismogram and wavefront snapshots. Let's take a look of them, but first let's adjust the visualization options. I will add auto gain to the seismic gazers. And the VSP method is good for studying how the wave propagates in the medium, because the receivers are placed directly in the medium that being studied, and we can match directly each event, such as a change in velocity in the layer and the formation of the reflected wave, to the exact position along the depth of the section. We see that while wave propagates within one layer, here, the angle of the first arrivals line does not change. And this corresponds to the constant velocity in this layer. As soon as the wave touches next layer, a reflected wave is formed on the seismogram here. And also we can see that the angle of the travel time curve changes. And this corresponds to a change of the velocity in the next layer. And more complex pattern is formed when the wave in a high velocity layer begins to overtake the wave propagating along the wellbore. So here we can see two different wavefronts, two different lines on our seismic geyser. And this one is formed because this picture is formed because the wave that moves through the high velocity layer overtake this part of the wave, which was a little bit slower because it goes through this lower velocity layer. And here we can switch between different offsets. We have three sources here with different offsets from the borehole. As you can see, as the offset from the well increases, we can see that the line of the first arrivals at the top of the section distorts here. It's easily can be understood if you imagine the geometry of the waves that comes to the our receiver line. And let me also show you a model with a more complex geology. This is a pre-built model that you can find in programs folder templates. In addition to the complex geology, the model also introduces topography, all of which can be set by the program. I've already calculated the data for this model. So moving between the images, we can see how the wave picture gets more complicated and the wavefront passes the acoustic boundaries. And here you can see the seismic geyser for this model. And to reconstruct such a model from the field data would be a real challenge for the geophysicist, but it is the most often that such models we can encounter in our real works. As you model the data, you can obtain the seismic geyser that was calculated with this software, and you can try to process the data to understand will you or will you not obtain something that will remind you the original model. And this is how software can help you to understand the correctness of your method. Will it solve your problem? What is the best source and receiver step? And you can also create a presentation for your customer and justify to him why you choose this method, seismic works, and these parameters of survey, and how it can help him to understand the cross-section. That's all that I wanted to show you as a brief overview of the process of work in Tesseral. As you notice, it is quite easy to build the model in the program and to obtain the calculated seismic data. And now I will pass the word to Vladimir so that he can continue his presentation.
Thank you very much, Roman, for your beautiful demonstration of Tesseral Engineering. Let's continue my presentation. So I would say that you have seen that the full way for seismic data modeling is quite simple, and the process of setting of building of the model is quite quick. So let's go further to examples. This is the simplest example in this presentation. This is a snapshot for the acoustic wave equation, which means that we only set the compressional waves velocities for the model. We used an omnidirectional source here. It's omnidirectional. The model is very simple. There is only one boundary, and the source is placed inside the model. So this is boundary of the source. We see a very simple wave field here, which consists on reflected, refracted, and direct wave. So this is refracted, direct, reflected wave. So elastic modeling gives us more complex wave field that is much closer to reality. Here we set the densities and velocities of the compressional and shear waves. As a result, with an omnidirectional source, like in the previous slide, we additionally obtained converted waves here. If we use a source like a vertical monopole in elastic modeling, we will additionally get shear waves. No, more complex wave field, but it's more natural, like in the real medium. You have probably heard that there is a ray tracing modeling. It is implemented in Tesseral Pro. Perhaps in the future, it will also be added to Tesseral Engineering if our customers and clients would request us about that. To better understand what ray tracing is, let's look at the basic principles. The basis of ray tracing modeling is the calculation of ray paths propagating from the source to the receiver. In the ray tracing theory, the wave field is represented as a sum of waves propagating with local velocity along ray path defined by Snell's law. The principles of geometric optics are fulfilled, and the wave in the region of each point is assumed to be locally flat. And finally, in the presence of a single boundary, we assume that the amplitude of the wave is determined by the reflection coefficient for a plane wave or for the mirror angle of incidence. An important feature of ray tracing is the ability to simulate a reflected or refracted wave from a selected boundary. Here, this boundary is shown as a red line. We see rays that come out of the source, reflects, come out from the source, reflects, and returns to the receivers. Let's take a look at the difference between full wave and ray tracing modeling. There are several limitations to ray tracing. High frequency wave field asymptotics. This means that the waves propagate as if we are a very high frequency. Next is calculation within geometrical optics. In other words, we cannot calculate diffraction and other wave effects. And finally, dynamic in higher degree and kinematic in a lower degree. Distorted in parts of the model where the wavelength can be neglected. Ray tracing modeling doesn't allow obtaining continuous photographs, for example, on ledges like here. There will be a photograph break or so-called shadow zone. Full wave modeling doesn't have such a minus. On the right, you can see a snapshot of the wave field and the seismic gathers calculated by the full wave modeling method. So no breaks and continuous wave field. Obviously, in this model, ray tracing will not work very well, and we will not be able to get realistic seismic gathers as if we got them in the field, because here they have ledges, small objects. So it's too complicated for ray tracing. If we sublimate the pros and cons of these types of modeling, we get the following table. Two disadvantages of full wave modeling are the a bit longer calculation time, as well as the impossibility of calculating specific user-selected waves. In any case, all waves will be calculated, but nowadays computers are quite powerful, so a slightly lower computation speed in full wave simulations are not a significant disadvantage. Otherwise, full wave modeling is always better than ray tracing, but in any case, both are available in Tesseral. How do we usually use full wave modeling before the field survey? We create a geological model and calculate seismic gathers for our proposed system of observation. Then we process this data and see how well we managed to reconstruct the model. Here on a couple of slides are examples of seismic gathers and the models for various sections. We have changed only the depths or the boundaries and see how much the seismic gathers change. Analysis of this data allows us to choose the optimal system of observation in the field. Let's take a look on another example. Here is a rather interesting example, I believe, where we tried to understand how well we can see the faults and the reflected wave data on the reflected wave data at a different depths on a real project we're working on. The modeled faults of different amplitudes. So this is fault and boundary, and checked how they were reconstructed. This is 5 sections for different displacement. It can be seen here that such a fault is visible only with significant displacement of 20 or 40 meters. So, and we actually can see it here. If the displacement of the rocks occurred by the other direction, the fault is already visible at amplitude greater than 5 meters. So we can see this fault everywhere. And then we calculated a model that was close to the geological model on our real project. Here you see a set of slanted boundaries and velocities and depth scale here, and reconstructed cross-section. Here is a comparison of the real data obtained on the project and the reconstructed model without faults. Here, without faults, synthetic model, without faults. This is real model. The depth was up to 1 kilometer. And then we added faults to our model, our synthetic model, in order to understand how they will look on the sections and what amplitude of faults we can actually see. So 5 meters, 10 meters displacement, and 20 meters displacement. And so the conclusion is, like, we can see 5 meters displacement here, 10 meters, probably can, not maybe everywhere, and 20 meters, it's very obvious where is the fault. And on the left is the model data and what the faults look like. And on the right are sections from the real seismic data, these faults, this kind of faults. One more near-surface seismic example of data modeling. The task was to see if cracks can be seen in the retaining wall, which is under the dam embankment. In the model, we placed 3 cracks here with depths of 5 meter, 10 meter, and 15 meter for each cracks. The crack width in the upper part of the wall was 1 meter, 2 meter, and 3 meter. And a very common system of observation for near-surface seismic studies was used here. It was symmetrical split spread, 48 channels. Receiver spacing was 2 meters and 4 meters for source spacing. And signal center of frequency was set up as 60 hertz. It is pretty common center of frequency for source like a hammer, sledgehammer, which is very popular in near surface studies. And here the time sections of the CDP shows diffracted waves from the edges of the fracture, and after migrating, they disappear. And the presence of cracks in the supporting wall is diagnosed in the image obtained after the transformation of the migrated section into a depth scale with a supermost model. So we can clearly see cracks. That means that probably we have good chances to have successful project to solve this problem. To find cracks. Let's take a look on the next beautiful example. I really like it. This case of modeling that was done before the field project in Western Australia. The idea was to deliver water through the regional aquifer, so as not to build a complex and expensive pipeline system. To control this process, it was necessary to perform seismic monitoring, but how to understand whether it is possible to see the injected water in the seismic sections. Well, this model was built and seismic modeling was performed before water injection and after water injection into this layer. The modeling was performed in the exploding horizons mode using the elastic wave equation. The central frequency of the signal was 80 Hertz. This is a time section before and a time section after simulated injection. They seem exactly the same. But after subtracting the sections, we see the seismic effect of water injection. This means that there are good chances for this project to be completed successfully. Based on the results of the modeling, it was decided to start the project and it was completed successfully. So some brief conclusions. First is ray tracing and full wave modeling is a useful and powerful tool for solving a wide range of seismic problems. Second is currently this technology is not widespread for engineering seismic tasks, which is said for me. And finally, there are software solutions available on the market now is Tesseral Engineering that can break the situation and lead to the development and popularization of modeling technology among seismic professionals. You will get this presentation and you'll find here the links which the links to our website with descriptions of Tesseral Engineering, Tesseral Pro. And finally, I would say that we tried to show you very simple examples and models so as not to make the seminar complicated. But in fact, you can create models of absolutely any complexity. Here are some slides with such examples. With slanted layers, and folds. You can use borehole logging data to build a model. With thin layers, you can see it here, very thin. And finally, you can just enjoy the beautiful snapshots. I really like this modeling. I must say that you can use seismic data modeling at any stage of your project, during survey planning, data acquisition, processing, and during interpretation and mapping, and while building subsurface model, and during verification of subsurface model. So it's very powerful tool which will help you to have successful projects, to get more quality of interpretation or field data as well. In presentation, you will find my email here and my name. Please do not hesitate to ask me any questions by email. I want to add that Tesseral is the unique and great tool for teaching students as well. And probably the final slide. So it's let's say a couple words about how we use Tesseral Engineering in our work. In near-surface seismic surveys, we usually use modeling during interactions with client to justify proposed methodology, system of observation, or prove the need of changes in initial methodology suggested by a client. Usually client tries to save money and to make project cheaper, and sometimes it makes no sense because sometimes it's a way to get really bad, the worse result. So it's seismic full wave seismic data modeling is good tool to interaction discussion with your client, and usually that increases the cost of the contract, which is our main profit in my understanding. Moreover, I think that modeling increases our professional level in clients' eyes and increase the chances of getting the project, which is quite impossible. At least if I were the client, I would trust geophysicists who justify their ideas professionally with modeling rather than a company who just promises that they will achieve all the goals, right? I can see it at our work with our clients on survey projects. Sometimes we also use modeling for data interpretation, especially when working in difficult conditions that are very common for engineering surveys, seismic surveys. I'm convinced that in near-surface seismic, it is much more difficult to get optimum or very good data compared to oil and gas. The reason is the lack of resources, including worse project planning, less data, and commonly low level of knowledge among operators in the field, leading to mistakes and in decision on correcting the observation system. For example, modeling helps take geophysical knowledge of our company to a new level and makes every or almost every project successful. I can say that we are focusing a lot on survey projects. Sometimes we do it, but mostly usually they're quite difficult, so quite unique projects where we can't recommend our partners or our customers to client. And sometimes we know that this project requires a lot of equipment or maybe adapted equipment, let's say for cross-hole seismic tomography in mines, some really difficult conditions. And in that cases, we do a lot of seismic modeling. And I can't remember that we had unsuccessful project. And I think that the main reason of such a luck is a seismic data modeling. So I can see that in our work that gives a really positive result. And finally, when developing the equipment, we pay a lot of attention to modeling as well, and not only in seismic. That helps us get excellent data at test surveys. No doubt, this is a result of achieving better understanding of the method and fine-tuning for different geological sites. So if you have any questions, you can write them in the chat or in Q&A here in Zoom, or just email me. So my email here. So we have some questions in the chat. Migdalis Ramirez, with some presentation. Thanks, Vladimir. You're welcome, Migdalis. Thank you for joining us. So, Joanna, great webinar. Thank you, Joanna. What about geotechnical data modeling? Yeah, no problem. You can use Tesseral Engineering or Tesseral Pro for geotechnical data modeling. I can show you here. We have our own software, Geotech Control, which was developed specifically for geotechnical studies, for processing and interpreting data obtained by the seismoacoustic method of Syrian building structures mostly. And we did a lot of seismic data modeling for testing our software for testing geotech control, that it's work correct and that is solves all problems. And so next question. So yeah, can I use Tesseral for that type of modeling? Yes, Joanna, you can use it, no problem. Adrian Gomez, hello, thank you for the presentation. Can you tell us what is the difference between Pro and Engineering, between Tesseral Pro and Tesseral Engineering? So Tesseral Pro has no limitations. Tesseral Engineering has some of them. So maximum depth of the model is 300 meters. That would good enough in most near surface studies, and only 2D in Tesseral Engineering, and some limitations for quantity of a number of channels for every source. It's 101 channel in active spread, but no limitation for quantity of spreads. And so if you're working on in near surface studies and you're having just 2D, regular 2D seismic project, I would recommend you Tesseral Engineering. It's much more affordable than Tesseral Pro. Tesseral Pro, it's mostly for oil and gas, I would say, because it's 3D for really big models, larger depths, let's say. So no limitations there at all, but the price is higher. So what are the prices? The price for, yeah, it's really easy to check the price. Okay, please go to our international website. We have different types, but please choose international and go to software, seismic, and Tesseral Engineering. And here you'll find price for Perpetuum license. And we have some pay for annual fee for support, for technical support. And what else? So thank you, Adrian, for this question. Okay, do you provide discounts for universities? Yes, we do. Adrian asking us about that. So, Ivan,
yes.
can you ask, please? Can you tell about discounts for universities?
Yes, of course. Give me a second. So basically, for universities, even though that's the price for the commercial license is $5,000 per license, for universities, you could get 5 licenses, 5 full licenses of Tesseral Engineering for the same price.
Mm-hmm. Mm-hmm.
And we are really looking forward to cooperate with universities on various projects. Universities were historically a very good customers for us, customers and users. Many universities have used Tesseral Engineering as a part of the projects that are sponsored by oil companies. For example, University of Austin, University of Oklahoma, many other universities like this, many universities in Europe. And as a part of our university license, as a part of this price, we also provide one-day short training for the same amount. On Zoom, of course, not personal visit.
Mm-hmm. Okay, thank you. So we have one more. Okay, Adrian, thank you guys for a great presentation. Thank you, Adrian, for joining us. Thank you a lot. Thank you, everyone. Do we have more questions? Mm-hmm. So it seems to me that no questions anymore. Okay, so please do not hesitate to ask me through email, to send me questions, to send to all of us. We're here for you. Okay, it seems to me that we're going to end our seminar. Thank you, everyone, for joining us. Thank you, Ivan. Thank you, Roman. Thank you, Daria. Great work. Thank you. Have a good day.
Thank you, everybody.
Yeah, bye-bye.
Bye.
Thank you very much.
David, thank you. Thank you, David. Bye-bye.